Yes, new questions. Now, the fourth question, in the class we had proved that if you take a sphere, calculate the integral of the potential over this sphere, then it should be equal to the value of the potential at the center of the sphere. That was what we had proven. Now, in this question, well, we will be actually proving it. And how we will, well, try to prove, let's say. So we have these two concentric cylindrical shells. One has a radius A, the other one has a radius B. What is the potential of these cylinders? For a single cylinder, the potential it creates at the point, let's say R, is Q over 4 pi epsilon 0 logarithm of rho over rho 0. Which basically tells us that rho 0 is our reference point. Remember, when we are defining a potential, we have to choose a reference point. And rho 0 is the distance from the axis of the cylinder of this reference point. And if we can, most of the time, we just send rho 0 to infinity. But in this example, you cannot send it to infinity. That's kind of one problem we are having. And in the question, you were given that you take the potential at this point, at the center, to be 0. What is the electric field inside the cylinder? 0. So the potential of this point is equal to the potential of this point. So the reference point I can take to be on this point. So that is rho 0 is equal to A. So if for any point, this is for a single sphere, not two of them, a single one. So let's write the potential everywhere. No, it's not Q, by the way, it's lambda. V at the point R is equal to 0 if R is less than A. Do you agree? Because there is no electric field. Neither this cylinder nor the other cylinder creates an electric field. Okay, I forgot to mention it in the homework, but you can just assume that this has a charge density lambda, the other one has a charge density minus lambda. In this region, what is the potential? In this region, the potential created by this one doesn't change. There is an additional potential created by the inner cylinder. So the potential in that region is lambda over 4 pi epsilon 0 logarithm of rho over A if R is between B and A. What is the electric field outside? Remember, the inner cylinder has a linear charge density lambda, the outer one linear charge. The electric field is 0, so the potential doesn't change. So lambda over 4 pi epsilon 0 logarithm of B over A if R is larger than B. So this is the potential everywhere. Well, we are given, okay. I mean, even if they are conductor, nothing will change. So it's not written in the question. Now I'm telling you that the charge is uniformly distributed over the surface. I will add it to the problem. Now we have to evaluate. Now the theorem told us that V at the point R0 is equal to the average of the potential over the surface, this closed surface, which is a sphere with center at R0. And of course, we have to divide by 4 pi R cubed, R squared. Center at R0, radius R. So this is what we need to prove. We know the explicit form of the potential. Now, our theorem was valid for any kind of potential. Whatever the shape of the potential is, this should hold, whatever the potential is. Now, what we would like to prove is that we would like to prove that we would like to make a particular example of this problem. So let me take a sphere over here. This is my point R0. This is R. So V of R0 would be equal to V of R ds 1 over 4 pi, or let me do it the other way around. V of R ds 1 over 4 pi R squared. Let's look at this one. On the surface of this sphere, what is my potential on the surface? Lambda over 4 pi epsilon 0, logarithm of b over a, integrate over the surface, divide by the total area of my sphere. Well, these are all constants. I can take it out. Lambda over 4 pi epsilon 0, logarithm of b over a, ds 1 over 4 pi r squared. But this is nothing but the total surface area of my sphere, which is 4 pi r squared. But this is the potential at the point R0 also. Because R0 is out of both of these cylinders, and the potential is at R0 is lambda over 4 pi epsilon 0 logarithm b over a. Now this was kind of the trivial solution because the potential is constant everywhere. So its average is equal to that same constant. So that's kind of trivial. Now the difficult part will be, what if you take the sphere, let's say over here? Of course, the potential now is not a constant. It depends on where you are on the sphere. So you will have some complicated integrals. And eventually, when you evaluate those integrals, you will see that this theorem still holds. Yeah, that is for complex numbers in 2 dimensions. But in a sense, you are right. I mean, what Cauchy theorem states was that if you have a pole in a region, and if you evaluate your, not a pole, if you want to evaluate your function at a point, let's say z0, you evaluate it around you evaluate the integral of your function divided by z minus z0 around the contour containing that. But the difference is that contour could be arbitrary. Here, our surface cannot be an arbitrary surface. Our surface has to be a sphere. Otherwise, this result does not hold. It has to be a sphere. For example, if you think of Gauss law, when we were talking about discussing the Gauss law, if you have an enclosed surface, integrate the electric field over that closed surface, you get the total charge inside that surface. Gauss law is valid for an arbitrary surface. This is not valid for an arbitrary surface. This is valid only for a sphere. If you change your surface, this law doesn't hold. Furthermore, remember this law, when we were deriving this law, we used the fact that V satisfies every Laplace equation in the region that we are interested in. Not the Poisson equation, the Laplace equation. So this law we cannot use, for example, for such a sphere. Because for that sphere, in this volume or on the surface, it doesn't satisfy the Laplace equation everywhere. It doesn't satisfy it along this line. So if you integrate your potential over this surface, you won't get the value. The average will not be the value at the center of the surface. It will not be equal because it doesn't satisfy the Laplace equation. So these are basically, I mean, we have this result, but there are conditions that this result, and there are conditions for this result to be valid. One thing, the surface has to be sphere. If the surface is not a sphere, we don't have this equality. Second thing, the potential has to satisfy the Laplace equation on your surface. In fact, not on your surface, but everywhere inside your surface. If it doesn't satisfy the Laplace equation everywhere inside your surface, again, this equation is not valid. Because this result is valid only under those two assumptions, that your surface has to be a sphere and your potential has to satisfy the Laplace equation, not the Poisson. We did derive that. Check the notes. It's basically the potential at the center is the average of the potentials created by the other charges plus some term that is related to the total charge inside your sphere.
Hocam bir şey sor. Hani biz bu uniqueness teoremde şey dedik ya, işte bir tane şey var, işte Poisson'u sağlıyor dedik. Ondan sonra onu Laplace'a mı çevirip çözdük? Uniqueness'ı göstermek için.
Well, I mean, in the uniqueness theorem, one of the tricks that we are always using is that we assume two potentials. That is the solution. Each one is a solution of the same Poisson equation, but we look at their difference. The difference satisfies the Laplace equation. Now, our purpose in our strategy in proving the uniqueness is to show that the difference of these two potentials should be zero. So that is why we are always studying the difference. We first show that they satisfy the Laplace equation. In the first uniqueness theorem, for example, they satisfy the Laplace equation. And we know that the solutions of the Laplace equation cannot have a maximum or minimum. Then we show that on the boundary of our volume, they are zero, since both of the potential solutions should satisfy the same boundary condition. But that means since we have a solution of a Laplace equation which is zero all around the boundary, it has to be zero inside. So that kind of proves the uniqueness. That the uniqueness meaning that if we start with two solutions, the two solutions have to be the same everywhere inside our volume.
Peki elinde sadece bir tane potansiyel olsa, diğerini bilmiyorum, vermediler.
But we don't know what phi1 is. We don't know what phi2 is. What we know is that if somebody gives me two solutions of the Poisson's equation satisfying the same boundary conditions, for example, I know that those two solutions have to be the same. They might look different. We will have some cases where we will find many solutions that look completely different, but the uniqueness theorem tells us that they have to be the same. Now, what I mean by if they look different, for example, by one method, we can find the solution to have this form. I'm just being a bit schematic here. This is, let's say, one possible form of the solution. And somebody else tells me that the solution is this one. Now, let me put -1 to the end. And somebody else tells me that the solution is this one. They find it's in some other means. Then I can conclude that they are equal. We will see these examples. Don't worry. Now, in our you see, in our solutions using the method of images, we are already using the uniqueness theorem. Because what we are actually doing is we are just guessing one function, and then we are showing that our function, and we are just picking up some image charges out of our volume. So we are showing that our final result satisfies the Poisson equation in our volume, and it satisfies the boundary conditions at the boundary of our volume. But that solution, we just guessed it. It was just guesswork, basically. And then uniqueness theorem tells me that I am done. I don't need to search whether there are alternative solutions or not. I know that there are no alternative solutions. That is the only solution.
Dün şöyle bir şey yaptık ki burada tam ortada şey dedik, potansiyel sıfır mesela, elektrik alanı yoktu. O zaman
No, you see, potential equal to zero and no electric field are different things. You can have a potential equal to zero at a point, but the electric field need not be zero at that point. Because the electric field is not related to the value of the potential. The electric field is related to the derivative of the potential.
Yani hocam, yani sonsuzdan bir yük getirsem ben bu noktaya tam ortadaki yere, o zaman bir şey yapmamışım.
Well, that is your homework 2 question. Right? So you have a dipole and plus Q minus Q charge. And how much work would be done to move a test charge Q from infinity to the middle of the dipole? And you have the correct answer. You don't do any work. You don't do any net work.
Ama oradaki verdiğiniz potansiyel tam orta noktadaki potansiyel değil mi? Middle diye. Çünkü
No. I mean, you see again, let me repeat. We have this dipole, Okay, and we show that the dipole, the potential of the dipole looks like this one. This is true only if R is much larger than D. This is RD. You cannot use this result to calculate, let's say, the potential here at the center or anywhere nearby. This is valid only if I am very far away from my dipole. Now, the potential at this point, as you pointed out, is 0. At infinity, the potential is 0. So if I just move a charge from infinity to here, what is the change in the potential? There is no change in the potential, and hence there is no work done. Okay, now you should be objecting. How come there is no work done?
Orada kalan bir şey var aslında. Şimdi burada hani düşündüğümüzde aslında toplam yük 0 hani sistemde. Burada RD'den çok uzak olduğunda da hani aslında hiçbir şey yokmuş gibi olmaz mı? Niye böyle bir şey?
Well, depends on how far away. If you go to infinity, the potential is 0 anyway. But if you are not at infinity but sufficiently far away, it is not 0 but small. You see, if you would plot the equipotential, not the electric field lines, they look like this. They spread out, their density goes to 0. But nevertheless, if, let's say, if you are at this point, you are not at infinity, but you are sufficiently far away. Let's say 5 times the separation. That is sufficiently far away. At this point, the potential, there will be a non-zero potential that looks like this. Of course, if you go to infinity, you won't see anything. But even if there is a net charge, you won't see anything. And compared to, let's say, the potential of a point charge, well, I think this was squared, right? Not cubed. So compared for a point charge, this is the dipole. Point charge, 1 over 4 pi epsilon 0, Q over R. You see, the point charge also goes to 0 as 1 over R. For the dipole, it goes to 0 as 1 over R squared. It goes to 0 faster. As you said, the total charge is 0. Now let's come back to this one. How come the total work done is 0? So since the potential is non-zero, it's changing their electric fields around. The electric field should be doing some kind of work, right? So how come the total work is 0?
In some region, the electric field will resist reverse charge, and in some region, it will attract charge by itself. So this corresponds to plus work and minus work.
So, I mean, as your friend points out, depends on your path. I mean, if you just take your object along this path, along that line, the electric field is always in this direction. Your displacement is perpendicular to it. You don't do any work in any segment. But besides the paths that lie on this midplane, for example, if you consider such a path, in certain regions, as your friend points out, you will be doing positive work. In certain other regions in your path, you will be doing negative work. The total work will be 0.
Ama hocam mesela artı yük getirdiğin zaman o ortada böyle tutmak için enerji harcamam gerek mi?
You have to exert a force. Are you doing a work if an object is not moving?
EX'de düşününce
You don't do any work to keep an object. if I hold this like in this form, I'm not doing any work on the keyboard. I will get tired, but not because I'm doing work on the keyboard. I'm doing some internal work in my muscles. That's why I get tired, but not on the keyboard. For example, if you would just, let's say, tie my arm, this arm fixed, then I won't even get tired. I should still exert some force on the keyboard. Other questions about the previous topics we covered, previous homeworks, method of images?
Bir şey sorayım o zaman. Bu method of images'da çözdüğümüz sorular da genelde bir plate oluyor. O plate'in yüzeyi de sonsuz oluyor. Hani o sınır koşulları, nokta separation vesairesi sağlamak için.
Not necessarily. We also solve this problem. Nothing is infinite. We have a conducting grounded sphere, a point charge here, at a distance d. The radius was r. So everything is...
Şey sorusundan bahsediyorum hocam. Plate'de bir tane yük vardı yani.
Okay, so what you said was, in general, the plate is infinite. No. Well, that's one particular example where we have this infinite plate.
Yani orada çok pratik gelmiyor. Mesela method of images'ı orada kullanabilmem için plate'in sonsuz mu olması gerekiyor?
Yes.
İşte ama pratik hayatta hani sonsuz.
True. I agree. But you see, I mean, what do you mean by infinite? For example, if you have a plate, a finite plate, you put some charge over here, not a huge charge, a small amount of charge. Now, infinite just means, for practical purposes, very large. The size of the plate should be very large compared to my distance from the plate. So the electric field created by this point charge will be the same, more or less the same, at least the electric field created by this point charge in front of this conducting plate in this region will be more or less the same whether the plate is infinite or finite. It won't make any significant difference. If I'm only interested in this region, then I can use the method of images, assuming this is an infinite plate. And the error that I introduce will not be significant. Or, as I said, this is just one example where, as you said, in fact, we have an unphysical case. But this is something where we can actually create. You take a sphere. I mean, it's not so difficult to find a spherical conductor. And you bring some charge. Well, point charges do not exist, so you bring another sphere. And the problem of two spheres, even that problem we can solve using method of images.
Peki niye grounded yapıyoruz? Zaten conductor değil mi? Yani içinde zaten şey...
Well, you see, it doesn't have to be grounded. You see, this is one example. The second example, well, this one. Ungrounded. If it is not grounded, then we know that the potential need not be zero on the surface, but the total charge should be zero. So we said that, okay, so we put some charge Q over there. The solution of this problem is different. So we put some Q prime over here, and at the center we had to place a minus Q prime, where Q prime was Q times R over D, minus. The solution of that problem is different than the solution of this problem.
Yani yükün sıfır olduğundan emin olmak için böyle.
No, I mean, if you want to have the potential equal to zero on the surface, then you ground it. If you don't ground it, the potential is not zero on the surface, but the total charge is zero on the surface. And that's where the second uniqueness theorem comes into the game. So we know the total charge. Here we don't know the total charge, but we know the value of the potential on the boundary. That was our first uniqueness theorem. So it says that if you know the solution of the Poisson's equation with known boundary values is unique. So it is this problem. The second uniqueness theorem states that if you have a potential that satisfies the Laplace equation in a region bounded by conductors, and if you know the total charge of the conductors, then the solution is unique. So this is this one. Here we know that the potential satisfies, let's say, the Poisson equation in this region, and we know the total charge of the conductor. So the solution is again unique. And we said that the potential created by these three charges satisfies our Poisson equation in the region that we are interested in, and it does correspond to a total charge of 0 in my conductor. So it's the unique solution.
Hocam şimdi bu kürenin içine hiç Q prime falan koymasak, oradaki...
There is no Q prime in this sphere.
Hani hiç onu koymadan çözmeye çalışsak. Hani...
We will do that, don't worry. We will solve exactly the same problem without using the method of images. We will start it on Friday. Not this one probably, but we will start discussing it on Friday.
Ben aslında şey diye soracağım. Hani artı Q koysak, eksi Q'ları kendine çekecek kürenin bu tarafına. Bu tarafta artı Q'lar kalacak. Hani küreyi kaldırıp burada artı Q, eksi Q diye pointlar tıkıl düşünebilir miyim?
Well, you see, we don't care about the sphere. We don't care whether it's a conductor or not. The problem is, it is a system in which the charges can move. The potential will be created by the charges themselves, not the fact that we are in a conductor or not. If you know the final configuration of the charges, you can calculate the potential. But in this problem, at least we can simplify it a bit. The potential will be the same as the potential created by 3-point charges. Now, using these potentials, the potential, you can calculate the surface charge density. So an alternative way would be, if I give you the surface charge density and the point charge, then you can again calculate the potential. Let's calculate the surface charge density of this problem, not the other one. Well, we already know the basic steps. We have to first calculate the potential everywhere. From the potential, we have to calculate the electric field. And from the discontinuity of the electric field on the surface, we can calculate the potential. So that will be our strategy. Now, we had already discussed that this system, the potential created by this grounded conducting sphere with a point charge, is the same as if we put some Q prime charge over there at a distance d prime, such that Q prime should be equal to minus Q times R over D. Now let me define some vectors. Let me define the R0 vector to be D in the x hat direction. This I choose as my x direction. R0 prime vector to be at the D prime x hat direction. And again, D prime is nothing but R squared over D. Now this is what we had derived on Monday. No, not on Monday, yesterday. Now we can calculate the potential of this configuration. V is equal to Q over 4 pi epsilon 0, 1 over R minus R0, plus 1 over 4 pi epsilon 0, Q prime, which is minus Q R over D, times 1 over R minus R0 prime. Now let me choose a point over here. Sorry, I will make a change. I will call this one my z-axis, not x. So the charge is on the z-axis, the image charge will be also on the z-axis, and the center of my sphere is the center of my, the origin of my axis. So if I choose this point over here, I want to calculate the potential at that point. This will correspond to the theta angle of that point, theta coordinate. So r minus r0 will be equal to square root of r squared plus d squared minus twice r d cosine theta. And r minus r0 prime will be square root of r squared plus d prime squared minus 2r d prime cosine theta. So I basically know my potential everywhere in terms of the spherical coordinates. This is equal to q over 4 pi epsilon 0, 1 over square root of r squared plus d squared minus 2r d cosine theta, minus q over 4 pi epsilon 0, r over d, 1 over square root r squared plus d squared, d prime squared, minus 2r d prime cosine theta. This is my potential. And d prime, let me keep d prime as d prime for the time being. This is what my d prime is. I will put it eventually. Now the electric field is minus the gradient of V, of my potential. And if you look up the expression for the gradient of the potential in spherical coordinates, this is equal to minus del V by del R in the radial direction plus, no, there is minus 1 over R del V by del theta in the theta hat direction. There is no phi component because V doesn't depend on the phi coordinate, phi angle. The derivative with respect to phi is 0. Now I need to find the discontinuity in the electric field close to the surface. Now on the surface, I know that the electric field is perpendicular, should be perpendicular to the radial direction. Should be perpendicular to the surface. The electric field lines are always perpendicular to the conducting surfaces. That basically tells me that on the surface of this conductor, the electric field only has the radial component. So this is my ER at the point r theta. This is my E theta, again at the point r theta. So E theta, when r is equal to the surface, whatever the value of theta is, this is 0. Now you should check it explicitly that it is 0. So on the boundary of my sphere, the electric field only has the radial component. The electric field, when r is equal to r for any value of theta or phi, this is equal to minus del over del r, q over 4 pi epsilon 0, 1 over square root of r squared plus d squared minus 2r d cosine theta, minus r over d, 1 over r squared plus d prime squared minus 2r d prime cosine theta. I should take that derivative with respect to small r and then set small r is equal to capital R. Let's do that. This is q over 4 pi epsilon 0 r minus d cosine theta divided by, let me call this one r minus and this one r plus, r minus cube minus r over d r minus d prime cosine theta divided by r plus q. Now, sorry, this is r minus this one, r minus prime. In the r hat direction. This is the electric field on the surface of my conductor, outside. So this is outside. Electric field inside is 0. I'm inside the conductor, there is no electric field inside the conductor. So electric field outside minus the electric field inside should be equal to sigma over epsilon 0 in the multiply with n vector and hat, which is a unit vector pointing from inside to the outside. In this case, it is the radial vector, it is sigma over epsilon 0 r hat. So sigma over epsilon 0, if we write it out explicitly, this is q over 4 pi epsilon 0 r minus d cosine theta divided by r minus is r squared plus d squared minus 2rd cosine theta to the power 3 halves minus r over d 1 over r squared plus d prime squared minus twice r d prime cosine theta to the power 3 halves. Well, we can simplify this further. And to simplify it further, we have to use the fact that d prime is r squared over d. Remember, this was what we had obtained for d prime. And if you put it over there, you will see that there are significant simplification and you obtain the surface charge density.
Hocam bir şey soracağım. Hani kürenin içine Q prime koyduk ya. O zaman volume charge density'ye bir şey yapıyoruz.
You see, no. What we are doing is this one. The actual problem we have at hand is if you, let's say, if you put some plus Q charge over here and you are grounding it, there will be some additional negative charges on the surface. This is our charge distribution. What we are saying is that the potential created by this charge distribution outside my volume, the potential is the same as this configuration. That is the only thing I'm saying. I'm not putting a charge in my volume. What I'm actually saying is that this is the real charge configuration in my problem. What I'm saying is that the potential and hence the electric field in this region outside my conductor of this problem is the same as the potential created by these two charges in the same region. That's the only thing I'm saying. I'm not putting a charge Q prime inside my sphere. There are no charges inside my sphere. Inside the conducting sphere, you don't have any charges. The charges are on the surface. But this problem and this problem are equivalent. They are equal outside my sphere. I'm using that equality to solve for, because this is easier to solve. Here, I don't know what this charge distribution is. But by using this equality in this volume, I'm solving for the potential and hence the electric field in this volume. Inside, I already know what the electric field is. It is 0. The potential is also 0. And using so I know the electric field here. I know the electric field here. By using the discontinuity in the electric field, I can determine the charge distribution. And or once you determine the charge distribution, we could have calculated the potential straightforwardly from the charge distribution. If you use this charge distribution with this point charge, if you calculate the potential, you will get exactly the same potential that we had used, the one over there. Any last minute questions? Not a bad homework question. Okay, so see you on Friday.